So, in today's class we are going to be talking about red black trees. So, we are going to spend some time discussing what red black trees are, what is the relation to 2,4 trees is what we will discuss next, and then we will see the process of deletion in red black trees. It's going to be a slightly more involved process. So, we will be spending a fair bit of the class on deletion. In the next class we are going to handle insertion in red black trees. So, what is a red black tree? So, a red black tree, first it is a binary search tree, okay, and each node in a red black tree would have a, so we take the nodes of the binary search tree and we color them red and black, and then it becomes a red black tree subject to certain properties. So, first the root has to be colored black, okay, that is important. A red node can have only black children, that is another property that a red black tree has to have. If there is a red node, then its children have to be black. Now, one thing we are going to do is that in our binary search tree, if a node does not have a left or a right child, so we will create the left or right child by creating what we will call an external node, right, and I will show you what I mean by that. Right, we will create an additional left or right child. It might be that if it does not, so if it is a leaf node of the binary search tree, then it does not have either a left child or a right child, right. So, in which case we will put two external nodes below that leaf node, right, and make it the left and the right child, right. So, external nodes we are not going to color them. So, it is only the non-external nodes, the original nodes of the binary search tree that we are going to color red or black. We define the black depth of an external node as the number of black, its number of black ancestors, right. So, what that means is that we are going to take an external node and we are going to walk up the external node towards the root, and the number of black nodes we encounter is the black depth of this external node. And the one key property of a red black tree is going to be that every external node has the same black depth, and that we will also refer to as the black height of this tree. So, lots of definitions, but we will see what this means with a couple of examples, right. So, these are two examples of red black tree. Let us look at the one here. So, what do we have? This is a binary search tree on 5 nodes. I have colored the nodes black and red. The root is black. A red node has only black children. A black node can have black or red children, but a red node can have only black children, right. Now, as you can see, this node does not have any left or right child, this does not have any left or right child, this does not have any left or right child. So, I am going to add them, right. These I will call external nodes, they are not colored. So, all my external nodes in this class today will be shown with these square boxes, right. Now, what is the black depth of this external node? 1, 2. It has 2 ancestors which are black. Similarly, the black depth of this external node is 2, of this is 2, of this is 2, of this is 2, and of this is also 2. So, this is a red black tree.
They will be added only to the leaves or to the nodes with also one child?
So, we will add these external nodes also to nodes which have only one child, right. So, let us look at this example and that will be clearer here, right. So, once again the root is black. A red node has only black children, that is the key. Red node can have only black children, black node can have red children or black children, right. Now, we are going to add the external nodes. So, as you can see, this node has only one child. So, we will need to add an external node here also. Similarly, it will need to add 2 external nodes here and one external node here, and of course, these will take 2 external nodes and so on. So, these are the external nodes we will end up adding. Yes?
So, in the first example,
yes,
how come the root has a black, root is black and the right child is also black?
yeah, a black can have black children, but a red cannot have red children. It is not symmetric.
So, if we were to take the first case,
Yeah,
root has to be black and both the children left and right to be red.
right.
Then the right child, if we place 2 external nodes and we count the black height, so it will be 1.
Right. So, then it will not be a red black tree, that is what you are saying. So, if I had colored this red, then this would not be a red black tree. Yeah. So, the black height of this guy is 2. What is the black height of this guy, of this tree? 2. I take any external node and I look at how many ancestors are black, and you will see that it is 2 ancestors which are black, right. And this is true for every external node. If I look at this, it also has 2 black ancestors, this also has 2 black ancestors, and so on, right. So, this also has a black height of 2. Clear? So, what are the key things we have to ensure? First, that no red node has a red child. Second, root is black. Third, black height of every external node is the same. Black height or depth, I mean, I sometimes use the term depth to say how far it is from the top. So, black depth of every external node is the same. The black depth, that is what we will call the black height of the tree. Okay, depth of a node and height of the tree. Okay. Now, these are 2 examples of trees which are not red black. Why is this not red or black? This red child, this red node has a red child. So, this is not. So, even if I were to put in these external nodes like this would not be a red black tree. Why is this not a red black tree?
External node.
So, the problem here is what we call a double red problem, right. We will use this term quite often, double red, as in 2 reds occurring consecutively, one after the other. Here I add the external nodes, right. The black height of this node is, the black depth of this node is 2, of this node 2, of all of these it is 2, this is also 2, this is also 2, this is 1. So, this is the culprit. For this reason, this is not a red black tree, right. So, black height is not uniform, or black depth is not uniform. Okay. So, let us look at what the height of a red black tree is going to be. So, let us say h is the black height of a red black tree on n nodes, right. What does that mean? If I take any external node and I look at, count its number of ancestors, it has exactly h black ancestors. Okay. Now, when will the number of nodes in this tree, suppose I just tell you that this is a tree of black height h, when will the number of nodes in the tree be small? When the smallest?
All the ancestors are black.
When everything is black, right? You do not want anything red, you want as few nodes as possible, right. So, why include your red nodes and increase the number of nodes? So, let us have everything black. Now, if you have everything black, then this becomes a complete binary tree of height h, or my red black tree, because why? Because all the external nodes have to be at the same level now. If they have to be at the same level, all the external nodes, then it becomes a complete binary tree of height h. If I have a complete binary tree of height h, then the number of nodes in the tree is 2 to the h minus 1. So, the smallest number of nodes possible in a red black tree of black height h is 2 to the h minus 1. When is the number of nodes the largest? When would we have? When every black node has two red children, but the red node cannot have any red children, right. So, then it will have to have black children, which will have to have red children, and so on. So, we have these alternate layers of black and red. So, we start with the black, then we have a red layer, then we have a black layer, then a red layer, and so on. So, if the number of black layers is h, then the number of red layers is also h, right. So, the total height of the tree becomes 2h, and so the number of nodes in the tree becomes 2h minus 1, which is about 4 to the h minus, which is 4 to the h minus 1. Yeah. So, this implies that h lies between log of n to the base 4 and log of n to the base 2. So, just a plus 1 minus 1, you can figure out, right. So, if I give you a red black tree on n nodes, so I just turn the thing around, I am saying if I give you a red black tree on n nodes, then its height is at least log n to the base 4 and at most log n to the base 2, right. And we seen exactly the same property for 2,4 trees, right. We said its minimum height is log n to the base 4 and maximum height is log n to the base 2. The same kind of a thing is happening here. Is everyone with me? Okay. So, now you can immediately see that if I give you a red black tree, then to search in the tree will take how much time now? Log n. Why? Because it is first, remember, it is a binary search tree. So, it has the search property. So, I can do the search in the regular way, that is I start from the root, compare key with the root, go left or right and so on and on. Right. So, I can do my search, and the time taken for that search is just the height of the tree, and the height is no more than log n base 2. So, that is the time I take. Now, let us look at the correspondence between red black trees and 2,4 trees. So, in particular I am going to say that given any red black tree, I can convert it into a 2,4 tree. Okay. So, what are we going to do? We are going to take a black node. That black node, how many red children will it have? Well, it is a binary tree, right. So, it might have both its children could be black, one child could be red, the other could be black, or both could be red, both could be black, both could be red, one could be red and one could be black, right. Or both, you could have external nodes also, one could be an external node, but in any case the number of red nodes cannot exceed 2, it will be 0, 1 or 2, right. So, we are going to take this black node and its red children and combine them into one node, right. Now, how many keys will there become in this one node? At most 3. When both when this node had 2 red children. Yes, is this clear to everyone? Let us see. So, just to make sure, so what am I saying? I am saying we have a black node and we look at its red children. Suppose it had 2 red children, right. So, I am going to combine it into one node, all these 3 I am going to combine into one node. So, this one node will have 3 children. Suppose it had only one red child, right, then there would be 2 keys in here, and if it had no red child, then there will be only one key here. Okay. So, each node so formed has at least 1 and at most 3 keys. Now, furthermore, black height of all external nodes is the same. So, the resulting 2,4 tree, so in the resulting 2,4 tree all leaves will be the same, will be at the same level. Now, this might not make too much sense. What are we saying? Black height of all external nodes is the same. So, if I start from an external node and I go up the tree, the number of black nodes I encounter would be the same no matter which leaf I started from. And how many nodes? So, each of those black nodes is now part of a unique 2,4 node, yeah, because I took a black node and I took its red children and I combined it into one. So, each of the black nodes is part of a unique 2,4 tree node, a unique node of the 2,4 tree. So, as a consequence, when I start from a leaf and I go up to the root, I encounter the same number of nodes in the 2,4 tree, which means that all the leaves are at the same level of the 2,4 tree, right. We will show an example with which this will become clear. So, this is my red black tree, right. I am going to convert it into a 2,4 tree. So, I start with the root node, I look at its red children, it has 2 red children, right. So, all of these would combine into a single node, right, of my 2,4 tree. Great. Now, I am going to look at another black node, which is this, look at its red children, it has again 3 red children, 2 red children. So, all of these will combine into one, right. and they combine into 1 like this, right. Okay. Now, why is this? So, as you can see, when these combined into 1, these 4 links that are going out of this combination will be the 4 links going out of this node. Yeah. When I took this entire thing, let me go up. There are 4, 1, 2, 3, 4 children of this combined structure, right. They would be the 4 children of this node, right. So, this is the first one. Then I look at this, how many red children does it have? Only 1. So, they would combine into 1. So, I get another node which has 5, 7 in it. This becomes the second child, right. As you can see, this is more than 4. So, this will be more than 4 here, right. Now, what will be my third child? It would be just this black node, it has no red children. So, I create a node with only 11 in it, and the fourth one 19 and 17. So, I create another node with just 17 and 19 in it. So, this is the 2, 4 tree I get, right. Now, you can see the black height was 2, it was the same for every external, that was the black height, and I get a 2, 4 tree of height 2. Yeah. So, I am giving you a proof by example, but this should be clear why I will get a 2, 4 tree. So, the property of a 2, 4 tree, one critical property of the 2, 4 tree is that all leaves are at the same level, right. So, this is just saying that every node has 2, 3 or 4 children does not make it a 2, 4 tree. All leaves have to be at the same level, and that is ensured because of the fact that the black depth of every external node is the same here. Is this clear? Right. So, this is how we can obtain a 2, 4 tree from a red black tree. We can also go the other way around, that is, given a 2, 4 tree, you can make a red black tree. So, what are we going to do? We are going to take a node of the 2, 4 tree, replace it with one black node and then appropriate number of red nodes. What do we mean by appropriate number? If there were 2 keys in this 2, 4 tree node, then I will have 1 red node. If there were 3 keys, then I will have 2 red nodes. If there was only 1 key, then I will have no red nodes, and these red nodes will be the children of the black node. So, first I put down a black node and then I put the appropriate number of red nodes, right. Now, this ensures that I will not have a double red problem. Why? I will not create one red node as a child of another red node, because what am I doing? I am first taking a node of my 2, 4 tree, first putting down a black node and then putting 1, 0, 1 or 2 red children, right. And then when I take the next node of the 2, 4 tree, which is a child of the previous one, then once again I will first put down a black node, right. So, I will not have 2 reds consecutively happening, that will be seen in an example shortly. Furthermore, what is going to happen is that for every node of the 2, 4 tree I am putting in one black node, right. So, since all the leaves of the 2, 4 tree are at the same level, yeah, the black height of the resulting red black tree would be uniform, the black depth of all the leaves would be the same. Okay. So, let us take an example. Ignore this for now, this should have come later. This is my 2, 4 tree, right. As you can see, each node has 1, 2 or 3 keys, which means 2, 3 or 4 children, and the height of this tree is 3. Okay. Now, let us see, I will go. So, let us say this is the first node which I convert into a, so there is only one key here. So, I will just create a black node and nothing else, no red nodes, right. Now, let me take this one. So, I will create one black node and it will have 2 children, 2 red children, right. What should be the key in the black node be? 8, and 3 and 10 would be its 2 children. Yeah. Then I take this one. So, 18, just one black node with 18, no red children. Let me take 1, 2. So, this would have one black node and one red node, right. Now, I have an option. I might put 1 as the black and 2 as the red, or the other way around, right. So, I am going to put 2 as the black and 1 as the red, right. For 4, 5, 6, 5 will be the black and 4, 6 will be the red. For 9, black 9, nothing else. Here 12 black, let us say, and 11 red. 14, 15, 15 black, 14 red, and 20, 20. Okay. So, now are you convinced that you will not have a double red problem, right, just by the way we are doing things. When I take a node and I create something in the red black tree, I first put down a black node and only then do I put down a red node. So, at the next level, when I will first put down a black node. So, it will never have 2 consecutive reds. Furthermore, the black height of this red black tree. So, if I were to draw the external nodes and count their ancestors, so if suppose there is an external node here, it has 3 black ancestors, which is the same as the height of this red black tree. And because of that, all of them would have the same black depth, right. So, if I were to look at this external node which is here, then it has a black depth of 3. So, everyone would have the same, right, because if it is going from here to here, then it corresponds to going from here to here, because each of those black nodes is one level here. If you understand this perhaps. So, the black height is the same as the height of the 2, 4 tree. Is everyone with me? So, you understand what red black trees are, and you understand how they are related to 2, 4 trees. Basically, there is a 1-to-1 correspondence. Given any 2, 4 tree, I can create a red black tree. Given any red black tree, I can create a 2, 4 tree, right. So, in fact, the operations of insertion and deletion in a red black tree are exactly the same as we do in a 2, 4 tree, right. So, we are just going to mimic those operations in this setting, right, and that was one of the major reasons for doing the 2, 4 trees. So, we are going to mimic the operation, but of course, it will require to do it carefully to understand the. So, I am going to look at the operation of deletion, because this is the slightly more tricky operation. So, how do we delete in a binary search tree, right. So, the first step of deletion is the same as in a binary search tree, which is that you first search for the node, you identify where the node is. If the node is a leaf, then you just delete it, right. If the node is an internal node, then you find its successor or predecessor, you swap, and then you delete the successor or predecessor. So, now the successor or predecessor, suppose we were talking of successor. So, successor is a node which does not have a right child. Yes, if it does not have a right child, then that means that we would have its right child is an external node, right. We put an external node there, right. So, that means that the node that I am deleting, is always the parent of some external node. If it is a leaf, even then it is a parent of an external node. Otherwise, it does not have a right child if you were talking of a successor. If it does not have a right child, we put an external node there. So, it is always the parent of an external node, right. So, these are the 3 settings we could have of the node that we are deleting. These 2 correspond to it being a leaf, right. So, either the node is a leaf. So, if the node is a leaf, then either it is a red leaf or a black leaf. And the third setting is when the node that we are deleting does not have a right child, right. So, it does not have a right child. So, which means its right child is an external node. If it does not have a right child, but has a left child, then the left child, this left child has to be red. Why? If it were to be black, then the black height would not remain consistent. Yes. Why? Because if I look at this external node versus this external node, this if this were black, you follow what I am saying? If this were black, right, then if this node had 10 black ancestors, then this one would have 11 black ancestors. Why? Because all its black ancestors are also ancestors of this guy, and this has one more ancestor. So, this has to be red therefore, right. Now, if this is red, then it cannot have any red children, but it cannot have any black children either, because if it had black children, then once again we would have the same problem of black height not be the same. So, this is the entire structure that we would have. If this is the node that I am trying to delete and it did not have a right child and it was not a leaf either, then that means that its right child is an external node. We said that already. Its left child will be a red node, which would be a leaf. So, then in this case the node that we are deleting is really the parent of a leaf node. In this case the node we are deleting, in each case we are deleting this node here, right. In these two cases the node we are deleting are leaf nodes themselves, and in this case it is the parent of a leaf node. Yeah? Yes?
Sir, is the scenario in which 19 would have been a red node and 17 would have been a black node, would it have been different from this?
19?
Not possible. 17 is black and 19 is red.
If 19 is a red node, can 19 be a red node and 17 a black node? Black height would not be the same. He is saying suppose this is red and this is black. Right, this is red and this is red cannot be, right, double red problem है ना. This is red and this is black. Well, इसके अगर 10 black ancestor हैं तो इसके 11 होंगे, ठीक है, तो ये भी नहीं हो सकता. Right? Okay. Sorry, right. So, now this is an easy case to handle. If I am trying to delete this node, what should I do? It is a leaf, just delete it, nothing to be done, right. It cannot create a double red problem if I delete this. So, that is what I have done, just delete, just replace this entire thing with this external node. Yeah, it cannot create a double red problem and it cannot also change the black height of any node, right, because it is a red node after all. Similarly, in this case is also easy. Why? What will I do? I am trying to delete this. Swap as in? I am trying to delete this 19. So, what should I do? 17 can move there and this entire thing can be removed. Yeah? So, I have not created a double red problem. इसके ऊपर जो था वो था, it's as it was before, right. And this, if this had earlier it had 10 black ancestors, it still has 10 black ancestors, right, and this node also has the same number of black ancestors as before. So, the only tricky case is this one really. Yeah. By the way, what do these two cases correspond to in the case of a 2-4 tree? This and this. What are we deleting? We are deleting, the key that we are removing is from a leaf always in a 2-4 tree, and this corresponds to the case when the key that we are removing is part of a node which has at least 2 keys. Yes? The key that we are removing, is in a node which has at least 2 keys, and that was a very simple case there, right? You remember? If I had a if this was my 2-4 tree node and this had keys, let us say 3, 5, 3 and 5, and I was trying to remove 5 or 3, then it is a very simple operation, nothing needs to be done. And this case as well as this case, both of them correspond to this. Why does this correspond to this? This is the node, right. Even here this has to have a black parent, and so this is the node then corresponding node in the 2-4 tree. And since this is the corresponding node, it might be even larger actually, it might even have 3 keys, this might also be red. राइट तो 2 या 3 कीज हैं कम से कम आपके 2-4 ट्री के नोड में और 2 या 3 कीज हैं तो डिलीट करना ट्रिवियल है। दिस however is the tricky case. This corresponds to a single key in your 2-4 tree node. Yeah. So in the 2-4 tree node, if I remove this key, then the node becomes empty. That's the problem. And here this would correspond to change in the black height. Right. So hence we can assume that the node deleted is a black leaf. That is, this is the only case which is really interesting for us. And removing this reduces the black depth of an external node by 1. And so in general we are going to assume the following. We are going to look at the following step, right, that there is some subtree whose black height is reduced by 1, okay, and we want to reorganize the tree to take care of that, right. Why am I saying subtree? Well, this is a subtree, right. What is going to happen is that as we do our reorganizing, this tree could become larger and larger, right, जिसका black height 1 से कम हुआ है, and we'll see that. Okay. So this is going to be a fairly it's going to have a bunch of cases, this procedure, right. So let me assume that this is the tree जिसका black height because of the deletion 1 से कम हुआ है, ठीक है. So what I am going to do, I am going to look at the parent. So this is the tree, इसका जो root है इस sub tree का, I am going to look at its parent. The parent is, let's say, has key A in it. So first I will check whether A is black or A is red, right. Depending upon this I will have 2 different cases happening. So if A is red, so this is the picture. So what about the other child of A? It has to be black, right. Let us say it is B, right. Now let us look at the 2 children of B, let us call them C, right. We do not know whether they are black or red.
So what is this A here?
A is just a name for this node, nothing else.
Which node?
This is the tree whose black height has reduced by 1, the subtree. I am just looking at the root of that subtree and its parent. So A is the parent of that.
But sir, the case we were interested in was when the node to be deleted was a black leaf.
Yeah.
How would it have a subtree then? It
Right.
would only have the external nodes which are non-colored.
We are moving upwards, reorganizing and moving upwards. So then it will.
Right. So let me just clarify this point. So what you are saying is we are interested in when we are deleting this black node, which has 2 external nodes, right, and this has some parent somewhere. When I delete this entire thing, I replace it with 1 external node here. So essentially this subtree, this is a subtree, right, this node and its 2 external node children. इसकी black height अभी क्या है, 1 है. It is getting replaced by this जिसकी black height 0 है. The problem, the why I have to formulate it this way is that this is going to, you know, in some cases what is going to happen is that this is going to expand this tree. Okay, as we see the, so just take this for now and we will see. So abhi if you are confused, then just think of this as a single node, right, with 2 children like this picture. You can think of this blue triangle as that, right, its black height has been reduced by 1. Okay, so this is one possibility. If this is red, then this child is black and we do not know what its 2 children colored are. The other is that if this is black, A is black, then B could be red or black, right. So depending upon what the color of B is, we will again have different cases. So here depending upon what the color of C is, we will have different cases. So one second. So these are 2 cases, either both of these are black, okay, that would be one case. So I have not shown them black, I am just showing you what the various cases are and then we are going to handle these cases separately, one after the other. So one case is when both of these are black, the other case is when one of these is red, right. So this is, let us say, red and this is one case for us. This is just a part of the tree, right? There would be a left subtree here, there would be some subtrees hanging here and so on, and of course, this will have something, this will have a parent and more happening up. This is the case when both are black. So, I have not shown them here, but this will be another case. Okay. Now, let us come here. Now, depending upon what B is, we will have two cases, red or black, right. So, if B is red, then this is the red node, then it will have a right child which is black, its right child cannot be red, right. So, this would be black, and now I am going to look at its two children, and depending upon what these two children are, right, I am going to have two more cases. And the other option is when B is black, in which case we will have two children, and depending upon what these two children are, once again we will have two cases, right. So, here there is one case when one of these two is red, so that is a case like this, and the other is when both of them are black, which means I will just look at this kind of a structure. Similarly, here there would be one case when both of them are black and when one of them is red. Sorry, one of them is red, then I will have this, and when both are black, I will have this. So, in this manner, this is just a kind of a starting picture to show you that there will be 6 cases that we will be looking at, and we will see what the tree reorganization has to be done. Right. So, I am going to refer to this as case 1.1, 1.2, this will be 2.1.1, so on and on, you understand what the. So, this is the first case we are going to look at, right. So, this is what the picture would be. So, A, B, C and basically A, B, C, yes, and this is the tree subtree whose height has gone from h to h minus 1, let us say the black height has gone from h to h minus 1. Now, what will be the black height? So, all these heights are now black heights. What is the black height of this subtree? I have written h minus 1. Why is it h minus 1? Earlier, this had a black height of h. What should be the black height of this? H minus 1, because there is one black node here already. Yeah, so this will have a black height of h minus 1. Similarly, this will have a black height of h minus 1. This will have a black height of h minus 1. Right? And there is a.
If a node is red, then at least one of them should be black, no? Its children.
If a node is red, then both its children have to be black. A red node cannot have a red child. Simple. A red node cannot have a red child. It's a double red problem. Right? The other possibility is that C is a left child of B, right? So, it's a symmetric thing. Yeah. And now, how are we going to reorganize this tree? We are going to reorganize this tree in this manner. So, it's basically a rotation, right? B goes to the top, A, C goes here, A comes there, and these I have not labeled these things, but you can understand 1, 2, 3, 4, 1, 2, 3, 4 in this order will sit there. Have you seen these kind of reorganizations when you are talking of AVL trees? Right. Now, what does this correspond to in the case of a 2-4 tree? Let us look at it. Oops. Okay. So, what this corresponds to, this picture is basically that this node was empty, right, that is why the height went down. In the parent node, I have an A and it is red, which means that the parent node in the 2-4 tree has at least 2 keys. नहीं समझ में आ रहा। देखिए इस सब ट्री का ये जो है रूट नोड ब्लैक है, दिस विल ऑलवेज बी ब्लैक। ओके, ये रोटेशन गलत नहीं हो रहा। व्हाई इज दिस रोटेशन?
Sir, C is greater than B. And you are taking to left hand.
नहीं तो उसके children चेंज हो जाएंगे ना, T1, T2, T3, T4.
Okay, so you are right perhaps. So you are saying A is here. मैंने ये इसके हिसाब से कर दिया है, ठीक है, तो आप इनको इसके लिए जरा सा डिफरेंट हो जाएगा, राइट? सो इट विल बिकम A, C and B, right? Thank you. So it's basically okay. So ignore this one. It's for this one, this picture. right. Now, let us see what this corresponds to in the case of 2, 4 tree, because that is where all of this motivation is coming from. So, this is a red node, which means its parent is a black. So, when I had created the 2, 4 tree node, I would have at least 2 keys in the 2, 4 tree node corresponding to this guy, at least 2, maybe 3, but at least 2. Yeah. So, that is this one. So, it could be either 2 or 3. I have put the A here. Now, in the 2, 4 tree node corresponding to this guy, actually I took this one. So, I would have B and I would have C. Yeah. So, I would have a B and I would have a C. So, I would have B and a C. Maybe there is another key if this guy was red, maybe, right. So, this is what the picture is. And then what do we do in the case of a 2, 4 tree? Well, I have a problem because I do not have any key in this node. What do? I borrow from my sibling. My sibling can lend me because it has at least 2 keys, right. So, it is going to lend me 1. So, one of the keys is going to go up from here to here and one is going to come down from here to here. Yeah. Okay. So that is exactly what is happening. So, यहाँ पे BC है, 1 goes up, let us say the B goes up, C remains here. So, yeah, when I am looking at BC,
So this is for that and this is for that. So this is
yeah, so this is corresponds to this, yes. Okay, so let me correct this in a second. So, what we are saying, suppose we were to keep this one in picture. So, let's remove this for now, okay, and then this should be C and this should be B. Yes, now it is okay. So, let us keep this in mind. Okay. Now, what is going to happen? We have C and we have B here. So, which is the one which is going to go up? C, right, and A is going to come down. So, in the new node that I get here, I would have only one key A. In the node that I have here, C is not going to be there, and in this node A will get replaced by a C. In this node A is the only key, so which means A is black. In this node B is one of the keys, and if there were one other key here, either B is the only key in this node, or if there was one other key here, then it is already sitting here, we do not have to worry about that. So, B becomes a black node here, right, and this C, why should C be a red node? Because there are more keys here. So, C can continue to be a red node. So, this is just for motivation, but if you were to just look at this, this is good enough. We have taken care of the height problem. This is my new recoloring, this was red, this is also red. So, there cannot be a double red problem. Why? Because there is a double red problem if the parent is red, right, but the parent is not red. If the parent is red, then there is a double red, but if the parent is red, then the parent of this was also red, which means that there was already a double red problem, right. So, this cannot, so there is no double red problem. Let us check the height business. So, this is height, black height is h minus 1. Now, what is the new black height of this subtree now? So, for all these external nodes it will be h, for all of these also it will be h, for all these it will be h, for all these it will be h. So, the black height is h. What was the black height of this guy? H minus 1 plus 1, h minus 1 plus 1, h minus 1 plus 1, and this was h to begin with. So, इसकी black height h थी और जो हमने नया बनाया उसकी भी h है. So, the problem is taken care of, right. We have not introduced double red and the black height has been restored. Okay. So, that was, what case was that? So, that was our very first case, right. Let me just show you. So, it was this one, this case here. So, we have to go through these 6 ones, right. So, we will quickly now start going through them. So, this is when parent is a red node. So, this is what is written. So, parent by parent I mean this is the subtree whose height has decreased. I am looking at the parent of its root, it is a red node. It has a child, if it has a child which is black, and that black child has this has a red child, then this is what we do. So, the other thing is when it does not have any red child, B does not have any red child, that would be a second case. So, let us look at that. So, B has no red child. In this case, the picture is A, B, and both of these subtrees have as their roots black children, right. Now, what, so this went from H to H minus 1. So, this has to have a black height of H minus 1, and this also has to have a black height of H minus 1, right. Why? Because originally the black height of this entire tree was H, yeah. So, this must be H minus 1, this must be H minus 1, right. And now, what are we going to do? Well, this swap of colorings, just this recoloring will solve the problem for us. I make this red and make this black. Yeah. What is the black height of the resulting tree now? H, right, which is what the original height was. Why does this not introduce a double red?
Because both are
I made this red. No, but this could be a red.
other case was already handled.
Yeah, that is why we had taken care of that other case first. Now, you understand? If any one of these were red, then वो हमने पिछले केस में हैंडल कर लिया होगा. ठीक है, अब आपको समझ में आ रहा है क्यों इस तरह से हम केस डिस्टिंक्शन कर रहे हैं. तो इसका मतलब ये दोनों ब्लैक हैं, तो अब डबल रेड की प्रॉब्लम नहीं रही. ठीक है. एंड व्हाट डज दिस करस्पॉन्ड टू फॉर आवर 2-4 ट्री पिक्चर? वेल, दिस इज द नोड जो खाली हुआ है, ये रेड है, तो इसका मतलब यहां पे एक और की है पेरेंट में कम से कम. ये ब्लैक है और इसके दोनों चिल्ड्रन ब्लैक हैं, तो इसका मतलब ये इकलौती की है यहां पर इस नोड में, राइट. दिस इज द ओनली की इन दिस नोड सिटिंग ऑल अलोन, right. And then what do we do? If this goes up, then this guy becomes empty. So, what do we do then? Merge. These two combine into one single node and one key comes down from above. Yes. So, what will the new node, the keys in the new node be? B from here, A from here, which comes down from above. So, this new node is going to have B A in it, which is what is being done here. This new node has B A in it. This will be one node now, right? I take a black and I look at all its red children. So, this will be one node with B A in it, right. So, there is a one-to-one correspondence between what we did in the case of 2-4 tree and what we are doing here, right, and that helps to clear things up. So, we have looked at both the cases when this guy, when the parent was a red. If the parent was a red, then we know this is a black. If this had any red children, we have taken care of it in the previous case. If this had no red children, then we have taken care of it now. So, now we go to the next set of cases when this parent is a black, right. So, parent is a black node. If parent is a black node, then this could be a red or could be a black. So, I am first considering the case that it has a red child B. If this is red, then this has to be black, yeah, and if this is black, then this may be red, may not be red. So, now again, so the two conditions I am making or two assumptions I am making is this is red first and that this is red. In the next case, I am going to consider that this was not red, that this was black and this was also black, that this node had no red children, right. And you see why this is required, right. You have already seen one reason why to consider whether a node has a red child or not. So, this is the picture. This height went down from H to H minus 1. So, what is the black height of this tree? This entire black height, that means, was originally H plus 1. इसकी हाइट ओरिजिनली ब्लैक हाइट h थी और ये एक और ब्लैक नोड है, तो इसकी पूरे ट्री की ओरिजिनली ब्लैक हाइट h प्लस 1 थी. तो इसका मतलब इनकी ब्लैक इसकी ब्लैक हाइट h माइनस 1 होनी चाहिए, दो है इसके पाथ पर, इसकी ब्लैक हाइट h होनी चाहिए, इसकी ब्लैक हाइट h माइनस 1, इसकी ब्लैक हाइट h माइनस 1, या. और अब हम करेंगे एक रोटेशन और ये बना देंगे. तो फर्स्ट लेट्स जस्ट मेक श्योर दैट दिस इज करेक्ट, and then we will see why we came up with this, and why we came up with this is justified by our 2-4 tree, right. Okay, so let us just check it is correct. So, first well, you can see here that B is less than A. So, B is on the left, C well, C lies between, C is more than B, less than A. So, C lies between B and A, and D is more than B, but less than C. So, D is more than B and less than C. So, it's the search property is okay. And 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 are just organized as before, right, they just go in the same manner. Now, this one is this one, right. So, it has now a black height of h minus 1. This guy is this, so it has a black height of h minus 1, and this one is the very first one, so it has a black height of h. So, now if you look at the black height of the external, black depth of the external node, so these guys will have a black depth of h plus 1, these will have h minus 1 plus 1 plus 1, h plus 1, h minus 1 plus 1 plus 1, h minus 1 plus 1 plus 1. So, the black height, black depth of all the external nodes are the same. So, that thing is taken care of. And as far as the double red problem is concerned, the only thing could be that, well, this is red and iska ye wala bhi red hai, but ye wala is the same as ye wala tree. तो अगर अब डबल रेड प्रॉब्लम अब है तो पहले भी थी, राइट, तो पहले हो नहीं सकती क्योंकि पहले तो आपका इट वाज अ red black tree and we had only made changes in this subtree, right. So, this is a valid thing and it takes care of the problem. Okay. Now, where is this coming from? What is the motivation? Well, again, this was an empty node, this corresponds to an empty node, this is my root, this is the parent node, this has A and this has a red child. So, it means that this has two keys A and B, right, and this has one child here which has two keys C and D. So, that is what is happening here, right. This corresponds to this node and AB corresponds to this parent node. And what happens now? I can, because my sibling has enough keys, it will lend me one. So, one of the keys will go up and A would come down, let us say, right. So, which is the key which will go up? The largest one, C would go up and A would come down. This is the picture we would have B, C, D, A. And what does this correspond to? This corresponds to exactly this, B, C here corresponding to this node, A this one and D this one. Yeah. So, everything is coming from the 2-4 tree idea. What you would have done in the case of a 2-4, this is a direct one-to-one correspondence, right. So, you can just use that thing to decide what to do here. So, what is the case we considered here? That this is black, we have also already considered the case when this parent was red, and then we made the assumption that it has a red child, then this has to have a black child, and we made the assumption that this is red. So, now we will get rid of this last assumption that this is red. That means that this guy has no red child, C has no red child, which means both of these are black. So, we come to that case, C has no red child, right, and so this is the picture. So, these are two subtrees, both of whose roots are black, right, and so this has to have a black height of h minus 1 because the entire black height was h plus 1 to begin with, same as before. ये h था और ये 1 था, तो पूरा h plus 1 था, तो ये h minus 1 होना चाहिए, ये h minus 1 होना चाहिए, ये h होना चाहिए. इसमें अब हम ये रोटेशन करेंगे, right, and we will see the motivation once again coming for true 4 trees. So, once again C is between B and A. So, B here, yeah, A is larger than B, C is more than B, but less than A. So, the binary search tree property is okay, and the same T1, T2, T3, T4 अगर हैं ये तो T1, T2, T3, T4 ये हो गए. ब्लैक हाइट्स चेक कर लेते, ब्लैक डेप्थ चेक कर लेते हैं. यहाँ जो एक्सटर्नल नोड्स हैं उनका ये h minus 1, 1 and 1, h plus 1 हो गया. इनका h minus 1, 1 and 1, sorry 1 and 1 हुआ तो h plus 1 हो गया. इनका h minus 1, 1 and 1, h plus 1 हो गया. और ये वाला ट्रीज ये वाला, तो इसकी ब्लैक हाइट h थी तो h plus 1 हो गया. ठीक है. डबल रेड प्रॉब्लम, ये रेड हो गया है तो इसके अगर कोई भी चिल्ड्रन रेड थे तो प्रॉब्लम है, पर वो हमारा पहले वाले केस में चला गया. वी assumed these are both black. ठीक है. Where is this coming from once again? Well, this is the node which is getting empty. The parent has A and B in it, and then this has one this has one child which has only C in it because both of its children are black. So now once again we cannot borrow, we have to merge, and merge में C इधर जाएगा और A ऊपर से नीचे आएगा, तो CA ऊपर बस B रहा which corresponds to this, ऊपर बस B रहा और ये CA एक नोड में चले गए. Tired, huh? We have 2 more cases to go. ठीक है? So C has no red child. Now what is the case left? We started with the assumption that B is red. So now we need to work with the assumption that B is black. Yeah, that was the assumption we went. B is red. So we come to B is black. ये B होना चाहिए था, इसको मैंने C कर दिया, खैर कोई फर्क नहीं पड़ता, right? This is the node we are talking of. This is black. So now again the next case, that it has a red child, that's one possibility, and the other is it does not have a red child. So if it has a red child, let's say this is red. अब इसकी पूरे की black height h+1 है, तो इसकी h-1 होगी, इसकी h-1 होगी, इसकी h-1 होगी. आपने जो है इसको ऐसे रोटेट कर दिया, h-1, 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 ये 1 है, ये 1 है और ये 1, ये पूरी की अब h+1 हो गई ब्लैक हाइट. यस, पूरे की ब्लैक हाइट h+1 हो गई. D is between C and A, so D is between C and A. Where is it coming from? Very simple. This is empty. A does not have any red child, which means that it is the only key in its node, and this has a red child, so that means that there are 2 here. So once again it is going to borrow 1 from here. So D is going to go up, A is going to come down, and we will have this picture. So D is the only key in its parent. This may or may not be the only key in its node, because this could also have been red. Yeah, but we are not bothered about that. C यहाँ पे भी कोई हो सकता है, but this would be the only key in its node because this node was earlier empty. अब कौन सी लास्ट केस बची? जब C does not have a red child at all. A, C, no red child. हाँ, तो अब इसकी हाइट h है, पूरे की हाइट h+1 है, तो इसकी हाइट कितनी होनी चाहिए? h-1 होनी चाहिए, तभी ये पूरा इसका h+1 हो जाएगा. ब्लैक डेप्थ इन लीव्स का, इनका भी ब्लैक डेप्थ लीव्स का h+1 होना है, तो इनका h-1 ब्लैक हाइट होना चाहिए. राइट, नाउ व्हाट डू वी हैव टू डू? C को रेड कर दिया. राइट, तो अब क्या हो गया? ब्लैक डेप्थ सबका कितना हो गया? h-1 + 1 h. पहले क्या था? h+1 था, घट गया, पहली बार ऐसा हुआ. ठीक है, अब आपको समझ में आ रहा है कि क्यों मैंने ये आई वर्क विद द अजम्पशन दैट दिस इज अ सब ट्री जिसकी ब्लैक है डेप्थ जो है घटा है, क्योंकि हम इस सब ट्री को प्रॉब्लम सॉल्व करने के चक्कर में हमने अब ये बड़ा सब ट्री बना दिया जिसका ब्लैक डेप्थ 1 से घटा है. तो अब हम इसके ऊपर ये सारा अप्लाई करेंगे, रिकर्शन नहीं. विल नाउ दिस इज द ट्री जिसका ब्लैक डेप्थ 1 से घटा है, तो अब हम इसके पेरेंट पे जाके यही सारा काम करेंगे. अगर उसका भी ब्लैक डेप्थ 1 से घटा तो उसके पेरेंट पे जाके ये काम करेंगे, एंड सो ऑन एंड ऑन. ठीक है, व्हाट केस डज दिस करस्पॉन्ड टू? This has only one single key, this neighbor also has only one single key. So you kind of combine both of them, they come here and the neighbor becomes empty, the parent becomes empty. So the parent becomes empty, so you have to then repeat the process for the 2,4 tree deletion in the parent, which means it either has to borrow from one of its siblings or it has to merge with one of its siblings and all of that. So there was the same kind of a thing happening in the case of 2,4 trees there, that the process continued up, right? The deletion process, you know, the parent became empty now, the parent node became empty, so you had to do something there, and maybe then again the parent became empty, so you had to do something there, and so on and on. It could go all the way up to the root, in which case you reduce the height of the tree at the end of the thing. So same thing could be happening here, except that here all we are doing is recoloring a node. ये ब्लैक से रेड कर दिया हमने, एसेंशियली 1 बिट ऑफ इंफॉर्मेशन इस नोड में जो रखा था वो चेंज कर दिया. 1 बिट चाहिए बस रेड और ब्लैक स्टोर करने के लिए. ठीक है, फिर ये हो गया, अब इसका पूरे का हाइट 1 से कम हो गया, तो अब हमने इसके पेरेंट पे जाके वही फिर से चेकिंग करनी शुरू कर दी, वो सारे केसेस चेक किए, अगर कोई रोटेशन से काम हो गया तो ख़त्म, डिलीशन प्रोसेस ख़त्म, और अगर नहीं हुआ, हम इस केस में फंस गए, तो हमें फिर से रिकलर करना पड़ेगा, ठीक है। तो इन वन ऑफ द 6 केसेस वी हैव टू गो अप, बट व्हेन वी हैव टू गो अप वी डोंट हैव टू डू टू मच वर्क, we just have to do one recolor, right? So that's the summary. So in all cases except this last case 2.2.2, so deletion can be completed by either some reorganizing, by some rotation or by some recoloring. एक केस में हमने पहले रिकलरिंग करी थी, रोटेशन नहीं करना पड़ा था, रिकलरिंग से ही खत्म हो गया था डिलीशन का प्रोसेस, ठीक है। पर इस एक केस में हो सकता है आपका डिलीशन खत्म ना हो. In this particular case, the height of the subtree reduces and so we need to proceed up the tree. But in this case, we are only recoloring the nodes. एक नोड का कलर रेड से ब्लैक से रेड कर रहे हैं बस.
ऊपर चलेंगे तब तो फिर कुछ भी हो सकता है.
हाँ, जब ऊपर जाएंगे हो सकता है अब नेक्स्ट लेवल पर हमें जो है रोटेशन करना पड़े, राइट? या अगर वहां पे भी प्रॉब्लम नहीं सॉल्व होती है तो रिकलर करना पड़ सकता है when go up, right? So what is happening is, why is this a very fast procedure? Because you have to do essentially one rotation only. अगर आपने कभी भी एक रोटेशन किया तो खत्म आपका. कब आपका प्रोसीड करेगा? जब ये रिकलरिंग करनी होगी. बट रिकलरिंग तो आप फटाफट कर सकते हैं. इट्स अ वेरी शॉर्ट. ठीक है? सो विच इज व्हाट मेक्स दिस प्रोसेस रियली फास्ट.
अगर एक बार हाइट कम हो गई तो अगर हम ऊपर मूव कर रहे हैं तो इन ऑल द प्रीवियस केसेस हाइट प्रिजर्व रहेगी.
हाँ, एक्सेप्ट फॉर दिस लास्ट केस, इन ऑल केसेस हाइट प्रिजर्व रही थी.
अब हाइट तो थ्रू आउट प्रिजर्व रहेगी तो टॉप तक ही जाना पड़ेगा.
नहीं,
लास्ट केस रिपीट्स अगेन एंड अगेन.
लास्ट केस यदि रिपीट हो रहा है तो एक से कम हो जाएगा.
हाँ, अगर लास्ट केस रिपीट होता रहा तो आपको टॉप तक जाना पड़ सकता है.
नहीं सर, लास्ट केस अगर करिए तो टॉप तक ही जाना पड़ेगा.
नहीं, ऐसा नहीं है. ठीक है, यू हैव टू चेक दैट.
लास्ट केस अगर किया तो वही तो केस आ गया जो कि हाइट एक से कम हुई और उसके बाद यहाँ वाले केस डिफर हो गया, नेक्स्ट उसके नोट पेरेंट नोट हो गया.
ठीक है, सो चेक दिस लास्ट थिंग if you are not convinced, but this is the entire process of deletion. So the next class we are going to look at the process of insertion. It's much simpler than this. So this was the harder one, right? But keep in mind, you don't have to remember it if you remember the 2-4 tree, which was much simpler to understand conceptually, right? So if you remember that, you will also be able to remember this process.